Olbers Paradox. If the universe is infinite, if stars are scattered without end across an eternal and boundless expanse, then the night sky should not be dark. This is not a poetic observation, it is a mathematical certainty, and for nearly 400 years it quietly threatened to unravel everything we thought we understood about the cosmos. The logic is almost childishly simple. Imagine standing in a forest that stretches forever in every direction. No matter which way you look, your line of sight eventually strikes a tree. There are no gaps. The forest, being infinite, fills every possible sight line. Now replace the trees with stars. In an infinite universe, every direction you gaze should terminate at the burning surface of a star. The entire sky, from horizon to horizon, should blaze with the accumulated light of an endless stellar population. Not scattered points of brightness against black velvet, a wall of fire. The night sky should be as bright as the surface of the sun, brighter even. It isn't. Step outside tonight, and you will see what you have always seen. Darkness. Vast, silent, pervasive darkness, broken only by the frail, lonely pinpricks of a few thousand visible stars. The universe appears to be ignoring its own geometry. This dissonance was first articulated in 1823 by the German astronomer Heinrich Wilhelm Olbers, though others had glimpsed the problem before him. Kepler worried over it, Halley tried to dismiss it, but Olbers gave it formal shape, and so it carries his name, this beautiful and stubborn contradiction between what the mathematics demand and what your own eyes report every single evening of your life. For generations, astronomers proposed elegant escapes. Perhaps interstellar dust absorbs the distant light, they suggested, acting as a kind of cosmic curtain. But thermodynamics is unforgiving. Dust that absorbs radiation heats up. Given enough time, it re-radiates that energy. The curtain itself would eventually glow. The darkness would return to light. That solution collapses. Others propose that the universe might simply not contain enough stars, that matter is too sparse to fill every sightline. But this only sidesteps the deeper question. It doesn't explain why an infinite cosmos would choose to be so sparsely furnished. The real answer, when it finally arrived, was far stranger and far more magnificent than anyone had imagined. It came not from optics or geometry, but from the deepest revelation of 20th century cosmology. The universe is not infinite in time. It had a beginning. Approximately 13.8 billion years ago, space and time and energy erupted into existence from a state of unimaginable density. The Big Bang was not an explosion within space, it was the birth of space itself. And this single fact demolishes the paradox with surgical precision. Light travels at a finite speed, 300,000 kilometers every second, which sounds impossibly fast until you measure it against the sheer scale of creation. Because the universe has a finite age, there is a horizon beyond which light has simply not had enough time to reach us. Stars may exist beyond that boundary, almost certainly they do, but their light is still in transit, still crossing the expanding gulf between there and here. We cannot see them. We will never see them. The observable universe is a sphere of visibility, and beyond its edge lies not nothing but silence, light that has not yet arrived. And there is a second blade that cuts even deeper. The universe is expanding, space itself is stretching, and as it stretches, it pulls the wavelength of traveling light along with it. Distant photons emitted as visible light billions of years ago have been elongated by this expansion. Their wavelengths dragged into the infrared, into microwaves, into radio frequencies our eyes were never built to detect. The light is there. It surrounds you at this very moment, but it has been redshifted beyond perception, stretched into invisibility by the growing architecture of space. So the darkness you see when you look up is not emptiness. It is evidence. It is the visible signature of a universe with a history, a cosmos that began, that is still growing, still rushing outward, still cooling from its original incandescence. Every dark patch between the stars is a window into the finite age of creation and the restless expansion that defines it. Olbers asked why the sky is dark. The answer turned out to be the story of the universe itself. The night is not a void, it is a message, written in the only language the cosmos knows. Silence where there should be light, and in that silence the unmistakable fingerprint of a beginning. The Vacuum Catastrophe. Everything in the universe, every galaxy, every photon, every atom vibrating in the marrow of your bones, exists within a framework of fields. Invisible, omnipresent, layered one upon the other like pages in an infinite book no one remembers writing. Electromagnetic fields, gravitational fields, the Higgs field, quantum fields for every particle that has ever existed or could ever exist. These fields are not passive backdrops, they are the architecture, they are what reality is made of. And even when you strip everything away, when you remove every particle, every wave, every whisper of energy from a region of space, something remains. The vacuum is not empty. This is one of the most confirmed and consequential discoveries in the history of physics. Quantum mechanics tells us with extraordinary precision that even the emptiest space seethes with activity. Virtual particles flicker in and out of existence on timescales so brief that no instrument will ever catch them in the act. Fields shudder and oscillate at their lowest possible energy state, what physicists call zero-point energy. You cannot remove this energy. You cannot cool it away. It is the basement floor of reality, and it is not zero. We have measured its effects. The Casimir effect, a subtle but unmistakable force between two metal plates placed a fraction of a hair apart in a vacuum, confirms that this energy is real, physical, and measurable. The Lamb shift, a tiny displacement in the spectral lines of hydrogen, agrees. Quantum field theory, the most successful predictive framework ever constructed by human minds, demands that the vacuum carry energy. The experiments confirm it. So far, so elegant. Now here is where the flaw gives way. When physicists sit down and calculate how much energy the vacuum should contain, when they sum the contributions from every quantum field across every possible frequency, they arrive at a number. And that number is not just large, it is obscene. The theoretical prediction for vacuum energy density exceeds the observed value by a factor of 10 to the power of 120. Let that land for a moment. Not 10 times too large, not a million times. 10 followed by 120 zeros. A 1 with a trail of digits so long that if you wrote each zero as small as an atom, the number would stretch beyond the observable universe. This is the vacuum catastrophe, and it is, by any honest accounting, the single worst prediction in the entire history of quantitative science. The theory works. The experiments confirm the energy is there. But when you ask how much, the answer that comes back is so staggeringly, absurdly, almost comically wrong that it defies every intuition about how a successful theory should behave. It is as though you asked a master architect for the weight of a house and received an answer greater than the mass of every star that has ever burned. And yet, the universe does not collapse under this weight. It does not fly apart. Space-time does not curl into knots. The cosmos, somehow, carries on with a vacuum energy so small, so finely restrained, that it barely registers against the gravitational budget of the observable universe. We know this because we have measured the accelerating expansion of space, driven by what we call dark energy, and the value we observe is breathtakingly modest. Almost, but not quite zero. Almost, but not quite. That sliver of difference, that whisper-thin margin between zero and the value we actually observe, is itself one of the most mysterious numbers in all of physics. Why not exactly zero? That would at least suggest some unknown symmetry, some hidden cancellation that wipes the ledger clean. But nature chose a value that is merely negligible, a residue so small it seems accidental, and so precise it seems intentional. Something is cancelling the vacuum energy with an accuracy of 120 decimal places, leaving behind only this faint, almost imperceptible remainder. We do not know what. We do not know how. No existing theory, not string theory, not supersymmetry, not loop quantum gravity, has produced a satisfying explanation. The vacuum catastrophe is not a failure of observation. It is not a failure of experiment. It is a fracture running through the deepest foundations of modern physics, a place where our two greatest theories, quantum mechanics and general relativity, meet and quietly refuse to agree. And in that refusal, in that enormous, silent, 120 order of magnitude gap between prediction and reality, there is almost certainly a door. One we have not yet learned to open. Poincaré Recurrence Theorem. There is a theorem in mathematics that no physicist has ever been able to refute. It was proven in 1890 by Henri Poincaré, a French mathematician who was trying to solve a problem about planetary orbits and instead stumbled into something far more unsettling, a truth about the nature of time itself. The theorem is precise, it is rigorous, and it says this: any system that is closed, that contains a finite amount of energy, and that obeys the laws of physics, will eventually return to a state indistinguishable from its starting point. Not approximately, not in broad outline, exactly. Every particle, every position, every velocity. Given enough time, the system will cycle back. Now, to understand why this works, you need to think about a closed system not as a machine, but as a deck of cards. A very large deck, but a finite one. The universe, if it is closed, if it contains a finite amount of energy distributed across a finite, accessible volume, has a finite number of possible arrangements. Enormous, yes, a number so large that writing it down would require more digits than there are atoms in the observable universe, but finite. And a finite system, evolving through time, is a system that must eventually revisit old configurations. For the same reason that a man trapped in a building with 10,000 rooms, walking randomly from door to door for eternity, will eventually find himself standing in every room again, and again, and again. The timescales involved are not human. They are barely even cosmic. We are talking about durations so vast that the current age of the universe, 13.8 billion years, registers as less than a single tick of the clock. The estimated Poincaré recurrence time for a system resembling our observable universe is on the order of 10 to the power of 10 to the power of 10 to the power of 76 years. That number is not large in the way a mountain is large. It is large in the way that language fails. Your mind does not refuse to comprehend it. Your mind never even gets close enough to refuse. But the theorem does not care about your intuition. It cares about proof. And the proof says, wait long enough and everything returns. The stars reignite in their original positions. The planets coalesce from the same dust in the same orbits around the same suns. Somewhere, on a small blue world, the same molecules fold into the same proteins. The same neurons fire in the same sequence, and a consciousness identical to yours in every measurable respect opens its eyes and believes, with total conviction, that it is experiencing this moment for the first time. It is not. Here is where the physics begins to press against something older than physics, something that lives in the marrow of how we understand ourselves. Because if recurrence is real, then the notion of a unique event dissolves. Every first kiss has been a millionth kiss. Every death has been a temporary arrangement. Every revolution, every discovery, every moment of private grief or unexpected joy is not a point on a line, but a bead on a ring, sliding past the same position over and over in a silence so total that no mechanism within the system can detect the repetition. The universe keeps no record. There is no counter-incrementing in the dark. Each recurrence is, from the inside, indistinguishable from originality. This is not the same as saying nothing matters. That conclusion is available, but it is not required, and it is not the interesting one. The interesting conclusion is structural. It means that history, all of it, from the first fraction of a second after the Big Bang to the evaporation of the last black hole, is not a narrative. It has no arc. It does not build toward resolution. It is a closed curve in an unimaginably high-dimensional space, and the arrow of time that we experience, that sense of moving forward, of accumulating a past and approaching a future, is a local phenomenon, a trick of entropy, a brief interval during which the deck happens to be sorting itself into a pattern we recognize as order, before the long, slow shuffle begins again. Poincaré did not set out to discover this. He was solving differential equations, but mathematics has a habit of answering questions that no one had the courage to ask. And the answer here is one that physics has spent more than a century trying to absorb. That in a finite system, given infinite time, there is no such thing as forever. There is only again. Quantum immortality. There is a thought experiment that physicists rarely speak about at dinner parties. Not because it's unscientific, but because it follows with chilling logic from one of the most respected interpretations of quantum mechanics ever written down. It begins with a simple, beautiful idea. Every quantum event has multiple possible outcomes. An electron spins up or down. A photon passes left or right. For nearly a century, physicists argued about what happens to the outcomes that don't occur. And in 1957, a graduate student named Hugh Everett offered an answer of breathtaking audacity. Nothing is discarded. Everything happens. Every possibility unfolds in its own branch of reality. A forking universe, splitting and splitting again, 10 to the 80th power times per second. Each branch as real and solid as the one beneath your feet. This is the many worlds interpretation. And it is not the fringe musing of a lonely eccentric. A significant portion of working physicists consider it the cleanest, most mathematically honest reading of quantum theory we have. Now apply this idea to something deeply personal. Apply it to your own death. Every lethal moment you will ever face, the speeding car, the failing heart, the misfired neuron, the silent tumour, is, at its foundation, governed by quantum events. Atoms colliding, molecules folding, electrical pulses racing along nerves. And because quantum mechanics permits every outcome, however vanishingly rare, there exists somewhere in the branching structure of reality a version of events where you survive. A cosmic ray misses the strand of DNA it would have shattered. A single ion channel opens a microsecond late and the heart finds its rhythm again. The driver, in some impossibly thin slice of probability, turns the wheel. In that branch, you wake up. Here is where the elegance becomes something stranger. Because consciousness, by definition, requires a conscious observer. The branches in which you die contain no future you to experience them. They are mathematically real, but subjectively silent. From the inside of your own mind, you can only ever find yourself in a branch where you are still alive. Always, without exception, forever. This is the idea known as quantum immortality. Follow it, gently, to its conclusion. You survive the illness that takes your friends. You survive the accident that should have been certain. Decade after decade, you find yourself improbably whole, while the people around you, who have no such guarantee from your perspective, fall away one by one. The branches you inhabit grow thinner, stranger, more finely tuned. You watch the century turn, then the next. You watch medicine extend life, then fail to extend it far enough for anyone but you. You watch nations dissolve. You watch the slow migration of humanity outward, or its quiet contraction inward. And still, by the arithmetic of branching realities, you remain. The sun swells, the oceans evaporate in some branches. In yours, something improbable spares you, perhaps a shelter, perhaps a fluke of orbital mechanics, perhaps a rescue you cannot explain. Earth becomes uninhabitable, and yet, in the impossibly narrow corridor of branches your consciousness is forced to occupy, you persist. Stars age. Galaxies drift apart in the expanding dark. The last reliable light fades. And you are still there, sustained by quantum coincidences so unlikely that they would, in any honest accounting, be called miracles. A body held together by statistical loopholes. A mind threading itself through the eye of a needle, again and again, as the universe cools toward its long, even silence. This is the unsettling gift of the many worlds interpretation, if it is taken at its word. Immortality, not as reward, not as transcendence, but as a consequence of arithmetic, a side effect of a theory designed only to explain the behavior of particles too small to see. Most physicists who entertain many worlds do not believe quantum immortality follows so cleanly. The definition of an observer, the continuity of identity, the measure of probability across branches, each is a door that can be closed against this conclusion. But the door does not close easily, and the question it leaves behind is one of the most beautiful and most quietly disturbing in all of modern physics. What exactly is the thing inside you that insists on waking up? Cosmic light delay and the causal disconnection. Look up tonight, and you are not seeing the sky. You are seeing its memory. Light, for all its impossible speed, is not instantaneous. It travels, it takes time, and every photon that strikes your eye has already finished a long, patient crossing through space before it arrived. The sunlight warming your skin left its source 8 minutes and 20 seconds ago. The sun you feel is the sun that was. If it had vanished while you were reading this sentence, you would not know for another 500 seconds. This is the first quiet truth of astronomy. Nothing you see is now. The moon you glance at is 1.25 seconds old. Jupiter, on a clear night, is more than half an hour behind the present. The nearest star beyond our own, Proxima Centauri, shows you a face from over 4 years ago. And Andromeda, that faint smudge of light visible to the unaided eye on a dark autumn evening, is a portrait painted 2.5 million years before any human stood upright to see it. The deeper you look, the older the picture becomes. The most distant galaxies captured by our finest telescopes are messages from 13 billion years ago, sent when the universe itself was still learning how to assemble matter into structure. The light has been travelling for almost the entire age of existence. It carries the appearance of objects that in the present tense almost certainly no longer resemble what we see. Some of those galaxies have since collided. Some have merged into vast elliptical giants. Some have torn themselves apart in waves of star formation, then quieted into long stellar twilight. Some perhaps gave rise to minds, civilizations, histories, entire chapters of thought and feeling that bloomed and ended while their light was still in transit toward us. You are not observing the universe. You are reading its obituary. And yet the obituary is incomplete, because the universe is expanding, and expanding in a particular way. Distant space stretches faster than light can cross it. This is not a violation of relativity. Nothing is moving through space faster than light. Space itself is growing between things, and once a region recedes beyond a certain horizon, no signal it ever sends can reach us. Not now, not in 1 billion years, not ever. We call this causal disconnection. It means there are entire provinces of existence whose news will never arrive. Galaxies whose final supernovae have already lit up skies we will never witness. Star systems that have already cooled into their own quiet endings. In a meaningful sense, vast portions of the universe have already finished their stories, and the final pages have been mailed to an address we cannot occupy. The observable universe, the sphere of everything we can ever, in principle, see, is shrinking in proportional terms with every passing eon. The cosmos is gently closing its doors one by one, leaving each observer on a smaller and smaller island of accessible light. So consider what this means for the universe you believe you inhabit. The night sky is a layered manuscript. The closest layers, recent. The middle layers, ancient. The outermost layers, primordial. Every direction you look is also a direction in time. Astronomy is, in the strictest sense, an act of archaeology. The telescope is a shovel. The photon is a fossil. The actual present tense universe, the one happening right now, in this exact slice of cosmic time, is invisible to you. It always has been. It always will be. No instrument will ever show it. No theory will ever fully recover it. The now of distant space is a country no traveller can reach, not even with light, not even with imagination disciplined by mathematics. And so we live, all of us, inside a beautiful illusion of simultaneity. A sky that feels present but is composed entirely of echoes. The universe you see is real. It is also, quietly, already gone. And the universe that is, at this very instant across the immense reach of space, exists only in equations and in the soft certainty that it must be there at all. The Doomsday Argument.
There is an argument,
quiet and unassuming, that has haunted the back rooms of theoretical physics for 40 years. It uses no telescopes, it requires no particle accelerators, it demands no data from distant supernovae or whispers from the cosmic microwave background. It asks only one thing of you, that you exist. And from that single, trembling fact, it derives the approximate expiration date of the human species. It is called the Doomsday Argument. It was formulated in 1983 by the astrophysicist Brandon Carter, the same mind who gave us the anthropic principle. And almost nobody talks about it. Not because it is wrong, but because, despite 4 decades of brilliant minds throwing themselves against its logic, it refuses to die. Let us walk into it slowly, carefully, because the floor here is thinner than it appears. Imagine a great urn. Inside this urn are numbered balls, 1 through 100. You reach in, blindfolded, and pull out a single ball. The number you draw is 73. Now, a question. How many balls do you think were in the urn to begin with? You could argue for 1,000. You could argue for 1,000,000. But the most honest, the most statistically humble guess is that the total was probably not vastly larger than 73. Because if there had been 1,000,000,000 balls, drawing the 73rd one would be an astonishing coincidence. And the universe, when pressed, tends to dislike astonishing coincidences. This is called the Copernican principle. The simple, devastating idea that you are not special. That your position, in space, in time, in any sequence, is most likely typical, average, unremarkable. Now replace the balls with people. Every human who has ever lived can be assigned a birth number. The first anatomically modern human is number 1. You, listening right now, are somewhere around number 108 billion. That is the running total. 108 billion human beings have drawn breath on this planet since our story began. Here is where the elegance turns cold. If you assume you are a randomly selected observer from the complete set of all humans who will ever live, past and future, then by the same logic that estimated the urn, your birth number is most likely somewhere in the middle of the final tally. Not at the dawn, not at the dusk, somewhere near the median. Do the arithmetic. If you are roughly in the middle, the total number of humans who will ever exist is something like 200 to 300 billion. We have already burned through 108 billion of them. At current population levels, with 8 billion souls alive at any given moment, the remaining quota gets spent in a handful of centuries. Not millennia, Not millions of years, centuries. That is the prediction. Drawn from nothing but your own existence and a refusal to believe you are cosmically privileged. Notice what this argument does not require. It does not require an asteroid. It does not require nuclear war, or a runaway greenhouse, or a grey goo nanotechnology accident, or a hostile artificial intelligence. It is silent on the mechanism. It only speaks of the timing. The universe, it whispers, does not need to tell you how. It only needs you to accept that you are ordinary. And here is the part that keeps philosophers awake at night. The counter-arguments have never quite worked. People have tried. They have argued about reference classes, asking who exactly counts as a human in this calculation. They have invoked the self-indication assumption, suggesting that the very fact of your existence makes large future populations more probable, not less. They have appealed to infinite multiverses, to observation selection effects, to the subtle mathematics of conditional probability. Each attempt chips at the edges. None has shattered the core. Because the core is almost embarrassingly simple. You exist. You are probably typical. Typical observers do not find themselves at the beginning of vast histories. Therefore, vast histories probably do not lie ahead. The logic is a closed circle, airtight, self-contained. It requires no faith in any model of the world beyond the assumption that you are not the protagonist of the universe. And perhaps that is why it is so rarely spoken of. Not because it is fringe, but because it is uncomfortably rigorous. A piece of pure reasoning that arrives, uninvited, at a conclusion no one wanted to derive. Carter himself never published it formally. He let it slip out almost reluctantly into the seminar circuit, as if he understood that some truths, once given a voice, are very difficult to put back into silence. The argument may yet be wrong. Somewhere, hidden in the assumptions, there may be a flaw waiting for the right mind to find it. But for now, it sits there, patient, mathematical, watching the clock. Wheeler's delayed choice experiment. There is a question that John Wheeler asked in the late 1970s that should not have an answer. It did, and the answer overturned something we did not even realize we believed. That the past is finished, that what has happened, that history, whatever else it may be, is at least settled. It is not. Begin with the experiment every physics student meets in their first semester. A single photon, a barrier with two narrow slits, a screen behind it. If you do not look at the slits, the photon behaves as a wave, passing through both at once, interfering with itself, painting a pattern of bright and dark bands on the screen. If you do look, if you place a detector at the slits to catch which one the photon traversed, the wave collapses. The photon becomes a particle, a single dot. The interference pattern vanishes. This is strange, but physicists made peace with it long ago. The act of measurement changes the system. Fine. The universe is shy. It performs differently when watched. Then Wheeler asked his question. What if you wait? What if the photon has already passed through the slits, already committed, already chosen its nature, and only then, in the final nanoseconds before it strikes the screen, do you decide whether or not to measure which path it took? The photon cannot know what you will do. It has already done whatever it was going to do. The dice, surely, have already landed. Run the experiment. The photon behaves according to your future choice. If you decide after the fact to measure the path, the photon will have traveled as a particle through one slit. If you decide after the fact not to measure, the photon will have traveled as a wave through both. Its past adjusts itself to match your present. This was a thought experiment for nearly 30 years. Then, in 2007, a team in Paris built it. They built it with mirrors and beam splitters and a quantum random number generator that made the choice so late, so impossibly late, that no signal traveling at the speed of light could have warned the photon what was coming. The result was exactly what Wheeler predicted. In 2015, it was confirmed again with single atoms. In 2022, it was pushed to even more rigorous extremes, closing every conceivable loophole. The photon's history is written by its observation, not before, after. Sit with this for a moment. The implication is not that we are deceived about the past. The implication is that the past, at the quantum level, is not a fixed thing waiting to be discovered. It is a cloud of possibilities, a set of histories, all of them real in some pale, unresolved sense, none of them chosen until an observer looks and forces the universe to commit. The past is a probability distribution. The present collapses it into definite history, and here, the wonder turns vertiginous. Because if this is true for a single photon in a laboratory in Paris, it is true for every photon, every particle, every event in the universe that has not yet been observed in some way that fixes it. Light from the early universe is still arriving at our telescopes for the first time. Photons that have traveled for 13 billion years, undisturbed, unmeasured. When they strike our detectors, we are not learning what happened. We are participating in deciding what happened. The Big Bang, in this strange and beautiful framework, is not an event sealed in the deepest archive of time. It is an unfinished sentence, a past that observers, by the simple act of existing and looking, are still completing. Wheeler called it a participatory universe, a cosmos that requires its observers in order to fully exist. We do not stand outside reality peering in, we are inside it, and our looking is part of its making. The universe is not a film already shot, awaiting our viewing, it is being developed in the watching. Tegmark's mathematical universe. Consider for a moment the strangest sentence ever written in modern physics. Mathematics is not a language we invented to describe reality. Mathematics is reality, and reality is only the part of mathematics we happen to be standing inside. This is the quiet thunderclap at the center of Max Tegmark's mathematical universe hypothesis. It begins with an observation so obvious we forget to be astonished by it. Every law that governs the stars, every equation that holds an atom together, every curve traced by a falling apple or a bending ray of light can be written in numbers. The universe submits, without protest, to algebra. Now ask the dangerous question. Why? Why should the cosmos care about our symbols? Why should a swirling galaxy obey a differential equation scratched onto a chalkboard by a primate on a damp planet? Physicists have called this, for nearly a century, the unreasonable effectiveness of mathematics. Tegmark proposes a resolution so clean it borders on the audacious. Mathematics works because there is nothing else. The universe is not described by mathematics. The universe is a mathematical structure. Full stop. And here the elegance turns vertiginous. Because if our reality is simply one self-consistent mathematical structure, made real by the sheer fact of its internal coherence, then there is no principled reason to privilege it. Every other self-consistent structure must be equally real. Every equation that does not contradict itself describes a world that exists somewhere in the fullest sense of the word. Consider what this implies. Somewhere, the gravitational constant is a hair stronger, and the stars burn out before life can wake up. Somewhere, atoms refuse to bind, and the heavens are an endless drift of cold hydrogen. Somewhere, time has two dimensions, and causality braids itself into knots no mind could untangle. Each of these worlds is not a possibility. Each is an actuality. They are not waiting to be born. They simply are. And this is where the listener's pulse should quicken. Because the same logic that grants existence to the beautiful universes grants it to the terrible ones. Worlds where suffering outweighs joy by unimaginable margins. Worlds whose physical laws permit minds to form only to be unmade. Worlds that flicker into being for a single mathematical instant, fully aware, and then dissolve. If consistency is the only entry fee, then the catalogue of what exists is not a museum. It is an inventory of everything that does not contradict itself. The good, the indifferent, the unspeakable. The hypothesis offers no exit. There is no curator deciding which equations are allowed to wear the costume of reality. The criterion is mathematical, not moral. And yet, hold the unease for a moment and look at what this idea actually accomplishes. It dissolves a question philosophers have wrestled with for 3,000 years. Why is there something rather than nothing? Tegmark's answer is breathtaking in its simplicity. Because nothing is a less stable concept than something. Because the absence of all mathematical structure is itself a kind of structure, and a fragile one. Existence, on this view, is not a privilege granted to a chosen few. Existence is the default condition of any pattern coherent enough to describe itself. We are not lucky to be here. We are inevitable. So is everything else. This is the strange consolation buried in the hypothesis. The universe we inhabit, with its warm stars and its liquid water and its improbable chemistry of memory and love, is not a fluke balanced on a knife edge. It is one note in an infinite chord, every note of which is sounding, right now, with equal authority. The terrifying universes exist. So do the radiant ones. So does this one, with you in it, listening to a voice describe the shape of all possible things. Whether Tegmark is right, no experiment may ever decide. The hypothesis sits at the trembling boundary where physics becomes philosophy, and philosophy becomes a kind of mathematics of awe. But if he is right, then the deepest fact about reality is not what is, it is what cannot contradict itself. And that, quietly, changes everything. The arrow of time. Consider the simplest, most stubborn fact of your existence. Coffee cools. It never warms itself. Glass shatters. It never reassembles. You remember yesterday. You do not remember tomorrow. Time, it seems, flows in one direction, like a river carved into the bedrock of reality, carrying every star, every thought, every heartbeat downstream toward a future that has not yet arrived. This is the arrow of time, and for centuries we believed it was the most fundamental truth in physics. Then we read the equations more carefully. Here is the quiet scandal at the heart of modern science. Every fundamental law we have ever written, from Newton's mechanics to Maxwell's electromagnetism to Einstein's relativity to the wave functions of quantum theory, every single one of them works perfectly whether you run time forward or backward. The mathematics does not care. Play the universe's film in reverse and the equations remain flawless. The shattered glass leaping back onto the table breaks no law. The cooling coffee gathering its heat from the air violates nothing. Physics, at its deepest level, has no preferred direction. So where, then, does the arrow come from? The answer arrived through Einstein, and it is more disorienting than any ghost story. When Einstein finished special relativity, he handed us a geometry. Space and time, he proved, are not separate. They are stitched together into a single four-dimensional fabric called space-time. And inside this fabric, something extraordinary happens to the idea of now. Imagine two observers. One sits still on a park bench, the other glides past on a bicycle. According to relativity, these two observers, moving differently, will slice the universe into present moments at slightly different angles. What is happening right now on a planet orbiting Alpha Centauri depends entirely on how fast you are walking down the street. For the cyclist, an event there might be in the past. For the person on the bench, that same event has not yet occurred. Both are correct. Neither is wrong. The mathematics is unforgiving. And this leads to a conclusion so quietly devastating that physicists gave it a name. They call it the block universe. If your now and my now can disagree and both be valid, then every now must already exist. The past has not vanished, the future is not waiting to be born, they are simply elsewhere, like rooms you are not currently standing in. Time does not flow, it is. The entire history of the cosmos, every supernova, every first kiss, every last breath, sits frozen in a four-dimensional crystal, complete and eternal. There is no floor of time, there is no ceiling, there is no privileged present moment ticking forward, there is only the block. You, reading this, are not a single person moving through years, you are a long, shimmering world line stretched across space-time, an unbroken thread connecting your birth to your death, every version of you existing simultaneously, equally real, equally permanent. So why does it feel otherwise? Why does time seem to flow? Here, physics offers its most elegant confession. The arrow you experience is not fundamental, it is statistical. It emerges from a single, almost embarrassing fact about our universe. It began in a state of extraordinarily low entropy, a moment of impossible order at the Big Bang. Everything since has been the slow, magnificent unspooling of that initial tidiness into disorder. Your memories, your sense of becoming, your conviction that the future is open, all of it is the felt experience of entropy increasing along your particular thread of the block. The flow is in you, not in the cosmos. And yet, here is the strange consolation. If the block universe is true, then nothing that has ever happened is truly lost. Every person you have loved still exists, somewhere along their world line, laughing, breathing, real. The Cretaceous dawn still breaks, Cleopatra still rules, the first hominid still looks up at the first star and wonders. Time does not erase, time only hides. And perhaps the deepest mystery is not why time flows, but why we, alone among the furniture of the universe, were given the haunting illusion that it does. The simulation hypothesis, the matrix. Every second, your brain performs roughly 10 quadrillion operations, 10 to the 16th power, electrical signals leaping across 100 billion neurons, each one firing in precise chemical cascades that somehow, through a process neuroscience still cannot fully account for, produce the smell of rain on hot pavement, the ache of missing someone, the specific blue of a Tuesday sky in October. Your entire reality, every texture, every emotion, every half-remembered dream is being constructed right now by 3 pounds of wet tissue suspended in darkness inside your skull. You have never once seen the world directly. You have only ever seen your brain's reconstruction of it, a model, a rendering, and you have trusted that rendering so completely, so automatically, that you forgot it was a rendering at all. Hold that thought. Because in 2003, a Swedish philosopher named Nick Bostrom asked a question that takes that forgetting and stretches it until it breaks. The question was not metaphysical, it was not spiritual, it was, at its core, an exercise in arithmetic, a cold, clean, statistical argument published in a peer-reviewed journal built on premises so conservative that the conclusion feels almost rude. And the argument goes like this. Assume that consciousness can, in principle, be generated by computation. This is not a radical assumption. It is the working hypothesis of most of modern cognitive science, that minds are what brains do, and brains are, at bottom, information processing systems of staggering but finite complexity. If that is true, then a sufficiently powerful computer could, in theory, run a mind. Not simulate the outward behavior of a mind, run one. A mind that feels, that wonders, that hurts. Now extend the timeline. Give civilization a few thousand years, or a few million, a blink cosmologically, and ask whether the computational power to simulate billions of such minds might eventually exist. Current trends in processing power suggest this is not a question of if, but when. A single computer, operating at the theoretical limits of physics, using the energy output of a star, could run more simulated conscious beings than have ever lived on Earth. Every human who has ever been born, outnumbered. Bostrom's argument then closes like a trap. He presents three possibilities and insists that at least one must be true. Either virtually all civilizations destroy themselves before reaching that computational threshold, or those that survive choose, universally and without exception, never to run such simulations. Or the number of simulated conscious beings in the universe so vastly exceeds the number of biological ones that any given conscious mind, yours for instance, is overwhelmingly likely to be among the simulated. There is no fourth option. The logic is airtight. You can reject a premise, but you cannot escape the structure. And here is where the ground begins to feel less solid beneath your feet. Because modern physics, the very physics that built the transistors and fiber optics carrying these words to you, keeps producing results that rhyme uncomfortably with this idea. Start with quantum mechanics. At the subatomic level, particles do not possess definite properties until they are measured. An electron does not have a position, it has a probability distribution, a mathematical cloud of potential locations that collapses into a single point only at the moment of observation. This is not interpretation. This is the result of a century of experiments, from the double-slit apparatus to Bell's inequality tests, confirmed to 14 decimal places of precision. Nothing is rendered until something is watching. If you designed a simulation and you needed to conserve computational resources, this is exactly the shortcut you would build. You would not waste processing power calculating the exact state of every particle in the universe at every moment. You would calculate only what was being looked at. You would keep everything else as a wave of maybes and resolve it on demand. Now add another layer. Space itself appears to be granular. The Planck length, approximately 1.6 times 10 to the minus 35 meters, represents what seems to be a hard floor, a smallest possible distance below which the concept of measurement loses meaning. Our equations do not merely become difficult at this scale, they become nonsensical. Space stops being smooth, it becomes discrete, quantized, pixelated. The Fermi Paradox. Step outside on a clear night, far from the sodium glow of any city, and tilt your head back. Above you hangs the visible portion of our galaxy, a slow, luminous river of perhaps 400 billion suns. Most of those suns possess planets. Many of those planets sit in the gentle temperature band where water can pool as liquid. The chemistry of life, we now know, is not exotic, it is ordinary. The amino acids that built you have been found drifting in comets, locked inside meteorites, and synthesized in the cold dark between the stars. The universe, by every measure we can take, is a machine for making life. So where is everybody? This is the question Enrico Fermi asked over lunch in 1950, almost as a joke, and which has haunted physics ever since. Because when you sit down with the numbers, the silence becomes deafening. Consider the arithmetic. Our galaxy is roughly 13 billion years old. Earth is only 4.5 billion years old, which means countless stars and countless planets had a head start of billions of years over us. Now imagine a single civilization, just one, that develops modest interstellar travel. Not faster than light, not magic, simply rockets capable of reaching 1/10 of light speed, a target our own engineers can sketch on paper today. Such a civilization, sending self-replicating probes to neighboring stars, where each probe builds copies that fan outward in turn, would saturate every solar system in the Milky Way in roughly 10 million years. 10 million years, against a galactic clock of 13 billion. In cosmic terms, that is the blink of an eye. the flutter of a single page in a 1,000-volume encyclopedia. Any civilization that arose even a fraction earlier than us should have, by now, touched every world, including this one. Their machines should be in our asteroid belt. Their signals should saturate our radio telescopes. Their engineering should reshape entire stars into structures we could see from across the galaxy. And yet, we look, and we listen, and we find nothing. Not a whisper, not a glint, not a single anomalous pulse that survives careful analysis. This is the Fermi Paradox, the flawless mathematics of probability, multiplied across hundreds of billions of worlds and billions of years, predicts a galaxy that should be loud, crowded, and visibly engineered. The observational reality delivers a galaxy that appears, by every instrument we have ever built, completely and beautifully empty. Something, somewhere, is wrong with our assumptions. The proposed solutions are themselves a kind of poetry, each one rearranging your understanding of what it means to be alive in this universe. Perhaps life itself is the rare miracle, and the chemistry that came easily here is, elsewhere, the longest of long shots. Perhaps life is common, but intelligence is the bottleneck, an evolutionary fluke that occurs once in a billion biospheres. Perhaps intelligence is common, but technological civilizations are short-lived, each one igniting brilliantly and then extinguishing itself within a few centuries of discovering the atom. This last possibility has a name. Physicists call it the Great Filter. Somewhere along the path from lifeless rock to galaxy-spanning civilization, there is a wall, a barrier so difficult that almost nothing crosses it. The unsettling question is whether that filter lies behind us in some improbable evolutionary leap we have already made, or whether it lies ahead, waiting. But there are gentler answers too. Perhaps the older civilizations are simply quiet. Perhaps radio waves, our chosen language, are as primitive to them as smoke signals are to us, and the true conversations of the galaxy are conducted in physics we have not yet discovered. Perhaps they are watching us right now, choosing not to interfere, the way a careful biologist does not shout into the rainforest. Perhaps the galaxy is a library, and the rule of the library is silence. Or perhaps the strangest answer of all is the truest. Perhaps we are early. Perhaps the universe, at 13.8 billion years old, is still in its opening chapter, and the conditions for long-lived, complex civilizations have only recently stabilized. The heavy elements needed for rocky worlds took generations of dying stars to forge. The radiation storms of the early galaxy needed time to subside. Perhaps we are not the latecomers to a vast party. Perhaps we are among the first guests to arrive, standing in an empty hall, mistaking the quiet for absence, when it is really anticipation. Each of these answers reshapes your place in the universe. Each carries its own gravity, and the most extraordinary fact is that we do not yet know which is true. The data is still arriving. Every exoplanet catalogued, every spectrum analyzed for the chemical fingerprints of life, every minute of sky scanned for an unnatural signal, is a vote being cast in the greatest census ever attempted. The silence above you tonight is not empty. It is a question, 400 billion stars wide, written in a language of absence. And whether the answer is that we are alone, or that we are surrounded, or that we are simply early, the conclusion is the same. We are living inside the most important mystery our species has ever asked. And the sky, patient as ever, is waiting for us to listen harder.